Jump into the new stuff. Did anybody have questions from homework 3? Woody?
Number 3.
So it says, under ideal conditions, the bacteria E. coli can double every 20 minutes. Suppose you started with 2 E. coli cells under ideal conditions. Write them out, describe the situation. So, since this is a,
For this note, it say you no longer have permission to access.
Yes.
you have to go CID. I didn't change any of the permissions. It's something that happened on your end.
Okay.
I don't know what to do to fix it.
Just research will help.
Yes.
Okay, this will be after.
Yes.
Thank you.
Anyway, since it's a biological system, I'm going to use the model with the E in it. So 2 was the initial number of E. coli cells, and then my rate is doubling, so that's an R. Oh, and so R is 2, right? To double is 2. And then B set, or the thing we have to remember though, that T is in these increments of 20 minutes. So B asks how many would there be after 3 hours, so I have to convert 3 hours into 20-minute segments. So 3 hours is 180 minutes, which is 9 of these 20-minute segments. So I'm going to do 2 equals e to the 2 times 9. So that's this big number. And then it asks how long before there's 100 or 1 million of these things. So we're going to do that by graphing, just like we've done before. So I'll do 1 million. And then I'll do that function. And to set my window, I know that by the time t was 9, it was well over 1 million. We just saw that result there. So I'll go 0 to 10, should contain that. The minimum was 2. I'm just going to leave it at 0, though. And the maximum needs to be over 1 million. So I'm going to do like 1.5 million. There's my 1 million line. Here's my growth curve. So that's the intersection I'm looking for. So second, trace, intersect, enter, enter, enter. So that's going to be, t is about 6.56. But remember, those are the number of 20-minute segments. So really, I'm going to do 6.56 times 20. So really, 131 minutes. Megan?
What does it say under the 25 minutes? On like the top.
So the t is in these 20-minute segments.
It says
Increments, yeah. That's what I'm saying. Right? Because remember the t has to match the rate. So the rate is doubling every 20 minutes, so the time isn't in minutes, it's in these 20-minute increments.
So is that a 20 or a 25?
That's a 20.
Oh.
Allie?
Can you do number one where it's like y equals EX plus 3? It's like not the whole problem.
Oh, the graphing one? Okay. So A is 1, B is 1. I'm sorry, I didn't mean for an H to be there. There is no H's. And K is 3. Since A is positive and B is positive, it's growth. The horizontal asymptote is always y equals k, so in this case that's y equals 3. And then my x's, for these ones with the e in it, I'm always going to just do -2, -1, 0, 1, and 2. And to find the y's, I'm just going to type this into my calculator.
Wait, so what do you type in here for y?
Just for number 1, I'm just filling the values in for x. Right? Just like we did before. So there's my first y. There's my second y. And just rounding these to the 10th is
Oh,
fine.
I see what you're doing. Okay.
Right? And then my third y. My fourth y. And my fifth y. And then you just plot that stuff and draw the graph, right?
Okay.
I'm not going to do that. Is that okay? And then the domain and range. We know the domain is always all real numbers for all these exponentials. And the range is going to depend on a and k. So since the a is positive, we know we're going from k. What's going on here? Just freeze again?
I'm trying to do it.
Again? Which number 2? There's 2 of them.
The first one.
So the model, again, I'm going to be using the model with the e in it. So I have a equals, the initial amount was 100. The value for r, it's half-life, so that's going to be 0.5. And I know that this is decay, so it's going to be negative. And t is in these 28.5 minute increments, just FYI. So for part B, to find my value of t that I need, I'm going to take 200 and divide it by 28.5, and then plug that in. So about 3 grams would be left. And then to do part C, we'll graph this thing just like we did before. So 10, and then I have 100 times e to the negative, negative 0.5 times x.
Is it good?
Yes.
It's kind of silly, but where did you find E? Like, why would I find E on?
Second, and then the ln button. It's on the left side.
Okay, I got it. Sorry.
That's okay. So by the time we got to 200 minutes, that was less than 10. So I know that whatever the t was here was more than enough. So 200 divided by 28.5 was like 7 or something. So 0 to 10 is going to be fine for us. And then my minimum, since it's decay, should be 0. And my maximum would be 100, my starting amount. And so we'll just hit graph. So there's my 10. There's my decay function. So this is the spot right here that I want. So second trace, intersect, enter, enter, enter. So my t is 4.6. But that's going to be in terms of those 28.5 minute increments. So if I multiply that by 28.5, that'll give me the raw time. So 131.
Yeah.
Sure. Okay. So, new stuff for today. Today we're going to introduce the idea of a logarithm. So we're going to be kind of building up to that idea today. So let's say we have the equation 2 to the x is equal to 4. What's my value for x got to be here? Two, right? Because 2 squared is equal to 4.
Yeah, you're right.
And if I had, say, 2 to the x is equal to 8, what's x got to be? 3, okay. Well, what if I have 2 to the x is equal to 6? What does x have to be in that situation? You think 2.5. That's not an unreasonable guess, right? 6 is halfway between 4 and 8. 2.5 is halfway between 2 and 3. Let's check.
You can have like a decimal as an exponent.
Sure.
Okay.
But 2.5 isn't it. Should it be bigger or smaller than 2.5?
Bigger.
A little bit bigger.
Bigger. Okay, so maybe we try 2.7. That's too big. So maybe we
fraction.
2.6. Too big still.
2.52.
So yeah, let's try 2.5. Well, let's go in the middle and go 5.5. So we'll
Okay.
but, oh, too small.
So it has to be exactly.
2.57265.
2.7, still too small. Let's try 2.8. Still too small. Maybe 2.9. Hi. Thanks. Hallie and Haley. You guys got some thingy-majiggers here.
Which one?
Evans. So 2.59 is too big. So let's try 2.585 maybe. That's still too big. Maybe 2.85. So that's too small, okay. So maybe 2.5845. Too small. Too small.
Mr. Clue, is there something simpler you can do to figure this out?
Yes.
Uh-huh.
Try making it a little bigger. Still too small.
Is it even possible to get to the right?
Bigger. Still too small. So we're going to add some more to the end, and we can keep on going and doing this, right? So this decimal that I'm creating, do you think it's ever going to finish? Doesn't seem like it, right? Seems like that decimal is going to keep going on forever. Okay. Look at the digits in that decimal. Does it seem like the digits are repeating in any kind of a pattern? What's the pattern? I don't see a pattern, right? So what kind of number goes on forever and its digits don't repeat in any kind of a pattern? We have a special name for a number like that. Well, E is an example of that kind of number. Those numbers are called irrational. So some examples of other irrational numbers we've talked about would be E, or pi, or the square root of 2, or the square root of 3, or the square root of 5. Notice in all of those numbers, we don't call them by their decimal, right? We give them a name to represent them. We don't ever call like pi 3.14152, we don't list it like that. We call it pi. We're going to do the same thing here. We're going to give this number a name. So the name we're going to give this number is log base 2 of 6. And what this is basically saying is this is the power of 2 that equals 6. So that's what that symbol is kind of saying. It's the power of 2 that equals 6. Everybody's okay with that? So this is something that you could do on your calculator. So to do this on your calculator, we're going to press the math button. And we're going to scroll all the way down to the bottom of the math menu and find the command that says log base. And then we can just type this in exactly the way it looks. So log base 2 of 6. And then press enter. And it'll give me a decimal approximation of what that is.
So if I did this decimal like squared, like that would be, no, wait.
So if I do
square, that decimal is-
2 to that power,
Yeah.
I get 6.
Oh, so you could actually do it, but like you say that.
Well, that number is infinitely long. the calculator is making an approximation because it has only so much memory space.
Okay.
Okay.
So to plug that number in, did you get like second, like second?
To get the ants there?
Yeah.
Yeah, the ants is the blue right here above the negative sign. So I press second to negative sign and it'll give me the ants, which is just the last thing you type, or the last answer that the calculator output. Woody?
When I press log, it doesn't give me the font for the 2.
So that's because you didn't go math and then go to the bottom and choose log base. Joe?
So there was a problem like this on the ACT practice thing I was doing, and it was like a negative number where the 6 is, and the calculator didn't do it. So are we not allowed to use negative numbers with the logs?
We're going to get to that, but yes.
Okay.
You can't take the logarithm of a negative number. So we talked about how to use the calculator to do one of these logs, right? This is what this does is it kind of gives us our definition for a logarithm. It says that log base b of y is equal to some number x is the same thing as saying b to the x is equal to y. So this side is like the logarithmic form, and this is the exponential form. So one thing we might ask you to do is convert back and forth using this definition from the logarithmic form to the exponential form. So if I give you an exponential equation like 3 squared is equal to 9, and I ask you to write that in the logarithmic form, so notice the b, the base of the exponential, is the base of my logarithm. So in this case, I have log base 3. The y is 9, and the x is 2. Everybody okay with that?
Yeah, that's not bad.
Let's do one more.
Yeah, that's not bad.
So here, again, like my b is 2, my x is 1/2, or I'm sorry, negative 1/2, and my y is positive 1/2. So what would I write? Oh, I'm sorry, my base is not 2. Goodness gracious. So log base 4 of 1/2 is equal to negative 1/2. I'm just using this rule up here to put the a or the b, x, and y in the right places. Okay. So we might ask you to go the other direction also to convert from the log form to exponential. 125. So log base 5 of 125 is equal to 3. So here my b is 5. My y is 125. And my x is 3. So I would say that 5 to the third is equal to 125. Everybody feel okay on doing this? Again, not terribly difficult. You're just using that little rule to rearrange things. So what that rule allows us to do, in addition to just rearranging things like this, we can evaluate some logarithms without using our calculator. So maybe we want to find log base 6 of 36. So what I'm going to do is I'm going to say, okay, whatever that number is, I'm going to call x. So b is equal to 3, y is equal to 36, and then I just have an x. So if I convert that into the exponential form, I have 6 to the x is equal to 36. What does x have to be in that case?
2.
2, right? Because 6 squared is 36. So that's what log base 6 of 36 is. Is everybody okay with that? Now, sometimes they'll be easy where you can do it on site. Sometimes it might be a little bit trickier. So let's say we have log base 4 of negative 1/8. So again, I'm going to think about whatever that number is as x. And then I'm going to rewrite this as an exponential. But 4 to the x equals negative 1/8. I don't know what the heck to do with that either, right? But what I can do here is I'm going to try then to rewrite these two sides so they have the same exponent base. So I notice that 4 is the same thing as 2 squared. And I notice that oh my goodness. I don't mean for this to be negative 1/8. I just want it to be 1/8. Jeepers creepers. Sorry about that. 1/8 is like 1/2 to the third, right? So if I have an exponent of an exponent, those can multiply. So I have 2 to the 2x. Everybody's okay there? And if I have a reciprocal like this, I can write that with a negative exponent. Like that. Everybody's okay there? So the rule I used was this one, right? From last chapter. So if I have 2 to the 2x equals 2 to the negative 3, the only way that those two numbers can be equal is if their exponents are equal, right? Since the bases are both 2, they the exponents would have to be equal, right? Everybody agree with that? So what I can say then is 2x has to equal -3. So x is just -3/2. Again, if you wanted to check that on your calculator, we could certainly do that. So math, log base 4, and then 1/8 is -1.5, which is 3/2.
How come you have to do it that way rather than just like the calculator?
I'm going to ask you to do things both ways.
Okay.
Okay? Not every logarithm you can do this way.
Yeah.
Some of them you can, and it's useful exercise to get used to using some of these exponent identities to kind of rearrange something to get into a different form to where we can use this logarithmic relationship. But yes, I fully admit that this is a problem you can do on your calculator. You should check on your calculator. Right? There's no reason not to do that. But we should also be able to kind of do the algebraic manipulation to get there also. Okay. So we've talked about how to evaluate a logarithm on your calculator. We've talked about the definition of a logarithm and done some examples of things you can use that definition to do. Let's talk about some facts about logarithms. That looks like farts. That's supposed to be a C. So the first one, as Joe pointed out, so if A is not positive, you can't take the log of it. You get an imaginary result. And we're never going to worry about what the imaginary result is in this class. That's beyond the scope of this class. So you would just say undefined or non-real answer or whatever. So you can't take the logarithm of anything that's negative, and you can't take the logarithm of 0. Which should make sense because the b is a base of an exponential, which is always a number that's greater than 0 and not equal to 1. So like, there's no way for me to get, it would be like saying, what power of 3 is going to give me a negative number? Well, like, nothing, right? You can't take a power of 3 of something that's positive and it become negative. You know what I mean, guys? So that's the idea there. Another one, log base b of 1 is equal to 0. If you think about this, what this is saying is just that b to the 0 is equal to 1, which that was an identity that we had last chapter, right? So that's just kind of a nudoi. And then the last fact we'll have is log base b of b is just equal to 1, which is an even more odoi, because all this is saying is that b to the first is equal to b. Well, yeah, of course it is, right? So next we want to talk about a little bit of notation. And this is really important notation. So So there are two special kinds of logarithms. The first one is called the common logarithm, and that is log base 10. But we're never going to write the 10 there. We're just going to write log with no base written at all, with no subscript at all. Because it's one that's commonly used, just like we don't write the 2 in the index for a square root,
Okay.
or we don't write the 1 in the exponent for any number, or a coefficient of 1 for any variable. We just like understand that it's there because we use it so much. It's like, let's just stop doing this. Is that okay?
Yeah.
And you'll notice that on your calculator, you have this common log as a button. Right? Here on the left side, you have log. So if I did log of 7, that is the power of 10. That gives me 7.
Okay, I understand.
The other special logarithm is called the natural logarithm. And that's log base e. But we don't ever write log base e. What we write is ln. You'll notice on your calculator right below the log button is the ln button. So like the natural log of 7 is the power of e that gives me 7.
Wait, where's the
Right below the log.
Oh, I'm sorry.
It's okay.
I thought you had to like go in like the math button again.
Nope. This is nice because these are on the home screen of your, like home buttons of your calculator. So I'm going to say this one more time. It is critically important that you memorize when there's no subscript on your logarithm, we understand the base to be 10. And when you see the ln, you understand the base to be e. These two logarithms get used a lot. You have to remember what the bases are because it's going to be, that's my expectation, is that you have that part memorized, okay? Kelly?
So like the logarithm, like where it's like log 5, 125, which one of those would that be the common? The common or the natural log?
That is neither.
Okay.
That's log base 5.
Oh, so that's a completely different thing.
That's a different logarithm than log base 10 or log base e.
Okay.
So it's the difference between like a square root and a cube root and a fourth root are all different kinds of radicals, right?
Okay.
Log, natural log, log base 2 are all different kinds of logarithms.
Okay.
It's kind of the same idea. Alexis?
It's just log basically like does that go to like ln or something?
ln is the letters there, yes. Joe?
So I know you said when we don't see a base, we have to assume it's 10. And then so when there's an e, does the e just stand for like infinite numbers?
So the e is that number from last lesson, that 2.71828,
Oh, okay.
yada, yada, yada.
Yeah,
That's the number e that we're talking about there.
Okay.
That same number e.
Okay.
Okay, so just as a little aside here, you'll notice that when I'm writing my logs, I'm using cursive when I'm doing this, right? When I write log and ln, I'm using cursive. I would encourage you guys to use cursive when writing your logs rather than printing. And I say that because in my experience, I've seen students on their papers where you have log of 3 becomes 10g times 3, and it becomes like 30g, and like we start doing weird things because all of a sudden the L and the O turned into a 10. Or when they had like ln of 3, that turns somehow into a 1n. So like 1n times 3 is equal to 3n, and like they start doing weird things and trying to solve for n. And so my suggestion to you is even if you don't regularly write in cursive, I don't regularly write in cursive. I would struggle to write anything in cursive, but I can write these 4 letters, L, O, G, and N in cursive and string them together. And I think will dramatically reduce like those kind of silly mistakes where you mistake an L for a 1 or a 0 for or O for a 0 or whatever. So I've been writing these in cursive on purpose. For that reason, also encourage you to do the same. Again, it's up to you, but I'm going to tell you right now that I would use the cursive, even if it's like that's kind of a hassle for me. It won't be a hassle after you do it 50 times in the homework or whatever. It'll just be doable. You know what I mean? Okay. So the big idea here, the big most important idea from this lesson is that we've now established a new inverse pair of operations. So like throughout your mathematics education, whenever you've learned one operation, shortly thereafter you learn its inverse operation, the one that undoes it. So like we start off with addition, and shortly thereafter you learn subtraction. Because addition undoes subtraction, and subtraction undoes addition, right? Next you learn multiplication, and shortly after that you learn about division, because again, multiplication and division undo each other. Everybody's still good? Then maybe you learn about squaring and square rooting, because again, squaring and square rooting undoes each other. Last chapter we talked about like exponents and nth roots. Again, these undo each other. Today, with this new identification of a logarithm, we have a new pair. So the exponent base, actually let's use the there, and a log base are inverses. So what we have here is that log base b would cancel an exponent base b. An exponent base b will cancel log base b. Just like adding 5 is going to cancel out subtracting 5. Or dividing by 7 is going to cancel out multiplying by 7. Or the 7th power is going to cancel out the 7th root. Is everybody okay with that idea? For that analogy anyways? Let's look at some specific examples here. So if I have log base 3 of 3 to the 5th, the log base 3 and the exponent base 3 cancel, and I'm left with just the exponent. Joe?
So can you only like cancel stuff out if the log base and then the
Exponent base
yeah,
match?
it's the same number, same
Yes.
value?
That is correct. So for example, if this was log of 3 to the 5th, there's nothing to do there.
And the base in that is 10, correct?
Correct.
Okay.
Because base of my logarithm, didn't match the base of my exponent.
So we can't even solve it, we just say nothing to do?
Well, there's nothing to simplify. You
Nothing to
can't,
simplify, okay.
right? You could type that into your calculator and get a number,
Right,
but that's not what we're asked to do here.
okay, right.
Right.
Cool.
So it's not evaluate, not find me the decimal and like. Is that okay with everybody? So the other way this would work let's say we have e to the natural log of x plus 1. Here, the exponent base e cancels the log base e, and we're left with just whatever was in the logarithm. Everybody okay with that idea? This is the single, I think, most important kind of conceptual connection that we need to make sure that we have when it comes to these logarithms. So this idea of how to cancel out a logarithm, or how can you use a logarithm to cancel out an exponent base, is, I think, the most important piece of this. Because if you can't do this, there's a bunch of different types of problems that are all going to become a problem for you later on. Specifically, like all of the solving stuff is going to be a mess if you don't have this concept kind of cemented.
You're talking about the simplified concept, right?
Yes, this idea that the logarithm cancels the exponent base and the exponent base cancels the logarithm.
Only if the two bases are the same value.
Exactly. So the last thing I want to talk about here in this lesson is just finding the inverse for a function. So this is something we did in first semester. So imagine we have something like y equals 2x plus 5. We'll take a very simple first semester idea here. To find an inverse, what we had to do is we had to get the x by itself, and then we switch the names of the variables. The x becomes the y, and the y becomes the x. So to get the x by itself, the first thing we want to do here be
Put it on its own side.
okay, get the x on its own side. So what would I have to do to get it by itself then?
Minus 5, right?
Yeah, we'd subtract 5 from both sides. And remember, we can't subtract 5, a number, from a variable, so we just write it next to it. And then we divide both sides by 2. And again, I can't divide a number with a variable, so I'm just going to write it right next to it. And then I just switch the x and the y's. And there we go. That's my inverse. Everybody okay with that? So let's do an example now that includes like an exponential or a logarithm. So let's say we have y equals 2 times log of x minus 1 plus 6. So again, we want to start by trying to get the x by itself. So the first thing I would do is
Can we add a 6 to the side with the y?
so I don't know about adding.
I mean,
but
like subtract, like add a negative 6.
yeah. but I knew what you meant. That's good. Okay. What next?
Can we divide the 2
Yes.
onto the side by with the y?
Yeah. So we can divide both sides by 2. Okay. Now we got to get rid of this log here, right? So what's going to cancel out that?
Can it cancel? Because the base is 10 and we have a
Okay, so the base on the logarithm is 10. That's good. We'll need that. So what can we do to both sides that's going to cancel out that logarithm? So remember, so what cancels out log base 10?
log base. Wait.
It's like
10.
Exponent base 10,
Um,
right?
yeah.
That's what it says here in the second statement. Okay, so what is that going to look like then for us? Is I'm going to do an exponent base 10 to both sides. Now you'll notice that I've written that 10 absurdly large. I did that on purpose because it's very easy to confuse this with multiplication. I am not multiplying both sides by 10. Right? 10 to the log is not the same thing as 10 times log. Everybody's okay with that? But the point of this is, because the bases match, those things can cancel out. And I'm left with just the stuff that was inside the logarithm. Everybody's okay with that? And so to finish this up, we just need to add 1 to both sides and have one note freeze.
Windows gonna act up for me too.
Not been happy. So again, I can't add the 1 to the 10 to the whatevers, right? So I just have to write next to each other. And the last step is just to switch the names. Is that okay?
So all you really did was replace the x and the y's.
Yep. All my x's turned into y's and all my y's turned into x's. That's my final step. Let's do one more. just don't understand. Like I'm not even, like OneNote's not even doing anything. And CPU percentage use is not even, like, absurd. Numbers I had in there anymore. Sorry if those numbers changed. I didn't remember what I'd written down before. Okay. Yeah, I don't. That's just what I'm doing. So sorry to everybody else. So one thing I want to establish here right away. Can I multiply this 2 and the 3 together and just call that 6 to the x minus 4?
Absolutely not. No.
No.
It says exponent.
Yeah, so remember,
What observation?
excellent. So remember, if you're going to multiply two things together, they either have to have the same base, in which case you can add their exponents, or they have the same exponent, in which case you can multiply their bases. Here, the bases are different. One is a 2 and one's a 3. The exponents are different. One is a 1 and the other is an x minus 4. Right? So you cannot combine those together. I see that happen frequently with students. So I just wanted to take a moment and establish that that is not something that's okay to do, that you have to be careful about how you're doing that multiplication. What should we do first?
Subtract 5.
Yes, sir. Next.
Divide by 2.
Yes, sir. Okay. Then what?
So is the 3x minus 4, is that a log? Or no, because
So the 3 is an exponent base.
yeah.
So to cancel that exponent base, we need to use a logarithm.
Okay.
Which logarithm do I need to use?
So 3.
I do not want to multiply by a reciprocal. That's not going to cancel out an exponent base. It's not 3 times x minus 4. It's 3 to the power x minus 4.
What if we use 3?
So if we take log base 3
Yeah.
of both sides, that's what we want.
Oh, yeah. Wait, so you just take like the 3?
Because it's the same as the base.
Yeah.
So basically that'll allow us to cancel out the 3 from the x minus 4.
Exactly.
So the problem's finished once you cancel everything out. You just have to flip flop that x and the y, right?
Almost. Because everything from the exponent is still left.
Oh, we have to put the 4.
Yeah, so we still have to add that 4 over. But after that, we just swap the variables and we are done. So
It's not that bad.
no,
It's just like a lot of steps.
it's just getting used to the steps.
I never played that game. No.
So cool. Can I ask you a problem that I had on my ACT thing?
Yes, 1 second though. First.
Yeah, no, you good. You good.
So your assignment here is going to be this worksheet 4.
Thank you.
So the first questions, I'm just asking you to use your calculator to evaluate the logarithm. So no big deal, just typing it into your calculator. Convert from exponential to logarithmic form, and then logarithmic form to exponential form. We did examples of those, right? I have some simplify the expression without your calculator. We did some examples of that. And then I have 3 of these, write the inverse and showing your work. And that's homework 5 or 4, excuse me. Okay, so we're gonna stop here now.
What?